so that it's like a refresher for you. Then we will see how the line sizing is done. And after that, the line list, how it is prepared and what are the various things coming in the line list. So first part will be line hydraulics. Generally, we say hydraulics means the study of flow through the piping and its characteristics, and then determining the sizing of the piping. So about 5th year completion of high fluids. So pipe theory, we'll see what is the pipe. Pipe is nothing but a tubular item. It's a circular conduit. It made of metal or plastic or glass, etc. Most of the apparatus in the laboratories, you must have seen, all are made of glass, pipes, beakers, conical beakers, measuring jars, etc. But when you come to the industry, glass is not feasible. One thing, you cannot make in big sizes. Second thing, it is fragile and breakable. It will break. So most of the piping in the plant are made of metals, different types of metals, carbon steel, stainless steel, monal, etc. Depending upon the service conditions and the nature of the fluid, corrosive nature, whether it is corrosive or non-corrosive. So metallic piping is mostly preferred. Plastic pipes are used for low temperature service, temperatures less than 100 degrees centigrade, because beyond 100, 130 degrees centigrade, plastic will be softening. It becomes soft and it may lose its properties, strength, etc. So only for, mostly for water services, you can see plastic pipes in water treatment plants and wherever we handle water. Okay. So this is meant for conveying. It can convey liquid, gas, or anything that can flow in the pipe. So it's a very important component for any industrial plant. It's apparently known. It is engineering plays its engineering is very important in the plant engineering. So overall engineering of the plant, piping plays a major role. So we will see next few slides, we will see and familiarize about the pipe and its components. So typical plant system, as we have seen in the earlier presentation, that we have number of equipment and they are interconnected by pipes to convey liquid from liquid, gas or vapor or a mixture of liquid and gas through the pipes. So you can see the example shown here is we have 3 tanks, tank 1, tank 2 and tank 3. 2 are vertical tanks, 1 is a horizontal tank. So how to connect? We want to make flow from one tank to other tank. So how do we make it possible? So to transfer fluid from tank to tank, we need pipes. So you bring the pipes. So now we have brought the pipes. You can see all the tanks are connected with pipes. But is it complete? No, we still need some more components to complete the piping. You can see pipes are coming closer, but how to interconnect them? We have to use some piping components. They are called fittings. Even in the household piping, you might have seen, we use elbows, we use T-joints, we use unions, we use reducers, expanders. These are all used to connect piping. Expanders or reducers are used when you connect 2 pipes of different size. If you want to connect a 10-inch pipe with a 6-inch pipe, you need a reducer. The reducer smoothly reduces from 10-inch to 6-inch. Similarly, 3 pipes are being joined means you need a T-joint. 2 pieces are joining. Straight means you will use a union or a coupling. It is in piping terms, we can call it as coupling also. But if they are at certain angle, you need a bend. It is called bend or elbow. Okay? So the fittings are very essential to make the piping complete. So now you can see, I told you, like this is a elbow. You have a T-joint because 3 pipes are getting joined. You can see a reducer here because this pipe is smaller than the other 2 pipes. So we need to put a reducer. Then there is a direction change. because this tank sits at a lower elevation. So you can see the pipe is traveling down, takes a direction change and then joins this one. Okay. The pipes and fittings are in place, but the ends are yet to be joined with the tank nozzles. So with tank nozzles, we can put flanges, normally flanges, because the vessel nozzle joint, okay, these points, tank 1, tank 2, tank 3, these joints should be removable. You must be able to dismantle. So we don't weld the joints. Other joints are all welded. You have to remember, these joints in industrial plant will be welded so that the joint is very efficient and leak proof. But when it comes to the equipment, we put a flange and bolting with the gasket in between to prevent leakage. So flanges will come whenever there is a nozzle in the vessel and external piping is connected. So you remember these names: elbows, bends. Bend is for longer radius, elbows may be shorter. So T's is the three pipes joining or branches. It may call it. You may call it. This pipe is branching into two. You can call it as branch sometimes. Reducers when it is from bigger size to smaller size. Expander is smaller size to bigger size. Coupling is two pipes when you join. Straight piece is coupling. Wallets, etc. So now. You can see the flange joint shown here. Here is the flange joint. Here is a flange joint. And you are seeing some more pieces in the diagram. You can see something, a valve with a hand wheel to operate. So valves are used to regulate the flow, either allow the flow or stop the flow or regulate the flow. You can vary the flow rate through the pipe by opening the valve, maybe 50%, 80%, or you can close it open. So valves allow you to regulate the flow through the piping system. And one more component you are seeing here is a filter or strainer. Sometimes the fluids may have solid particles, especially the pumps. When we put in the section of the pump, we put a strainer or filter to remove any solid particles. The solid particles will damage the impeller of the pump. So we have to remove the solid particles. So we use filters. There are a number of line items like this in the plant. So they are all called specialty items. Okay, specialty items. So the control is achieved through valves. So that's what we are seeing. There are different types of valves again. We have gate valves, globe valves, and check valves, butterfly valves. One more type is ball valve, which is very popular, very prominent in the oil and gas industry. The inside of the valve component is like a ball with a hole in the middle. It's a sphere. It's a rotating sphere with a hole in the central part, and that hole will allow the flow through the valve. Okay. So you just remember different types of valves are available, and the type of valve will depend upon the process requirement. Now sizing criteria, and most of you must have studied all your fluid flow theory. Then Darcy, we say Darcy Thompson is a scientist who lived between 1860 and 1948. He determined the fluid flow characteristics, how the fluid flow happens in a pipe. So you consider a pipe and you start with point 1 and you go to point 2. So for the liquid to flow from point 1 to point 2, some energy is required. It won't flow on its own. If you have a slope, maybe gravity will pull it. Otherwise, let us say all closed piping in the plant, we need to add some energy to the liquid so that it flows from point 1 to point 2. So the difference in energy is used to overcome frictional rate. Why we need to impart energy means we are forcing the liquid to flow through a pipe, and the pipe has a wall. It is a restricted path, I would say. So when it flows through the pipe, it has to rub against the walls of the pipe. So it loses some energy in that process that is called your friction. So when the fluid flows in a pipe, it loses some energy because of the friction happening during the flow with the walls. Okay. So you must have seen the velocity profile and other things. So what is the energy spent? Let us say 0.1 to 0.2. You can see the energy. You can just put a line here. Okay. It's like a manometer. So here energy is more, the liquid column is H1. By the time it reaches, it loses some energy. Here the liquid column is H2. So the difference between H1 and H2, this is HF. HF is the frictional loss. It's a head loss. Okay. This is how the fluid flow happens in the pipe. So sizing criteria, we use the velocity, pressure drop. These two are the important parameters in fluid flow. So Bernoulli equation you all know, the total energy of a flowing fluid to energy dissipation is expressed in terms of a head loss. Okay. That we have seen in the picture earlier. This is not a very useful without being able to predict the pressure losses that will occur in particular circumstances. The equations are good, but we have to apply these equations in the practical scenario. The most important mechanism of energy dissipation within the flowing fluid is introduced, that is the loss of total mechanical energy due to friction. So we have a factor known by the name friction. Again, because of the rubbing action of the fluid against a pipe wall, it's called friction, and we lose some energy. So in a steady flow of fluid, there is a frictional loss when the fluid flows. And for sizing, we need to know the number of parameters in the system. So one is the length of the pipe. What is the length of the pipe? That is the distance the fluid has to travel. Then diameter of the pipe. And U is the mean velocity of the fluid flow in meters per second. This is nothing but you know the fluid flow. Yes, somebody is raising hand. Okay, you can keep the questions. I will answer in the end. Okay. The velocity you can easily calculate. You know the volumetric flow. Say let us say meter cube per second through the pipe, and you know the diameter of the pipe. You can calculate the pipe cross-sectional area pi d square by 4. So divide the volumetric flow meter cube per second divided by pipe cross-section area meter square, you will get meter per second. That is the velocity of fluid flowing through the pipe. That is a mean velocity. Why we say mean velocity? If you see the velocity profile in the pipe, center of the pipe, the velocity is maximum because there is no friction. And it slowly reduces towards the wall, it will be on the wall, it will be 0. Okay, because of the friction. So there is a velocity profile when the fluid flow happens. So we get an average velocity of fluid flow across the pipe. Then mu is the viscosity of the fluid. You all know viscosity is another important parameter. And similarly density, fluid density in kilogram per meter cube. Here we have taken all in MKS unit, and then roughness of the pipe. So the pipe may look smooth with for a bare eye, means naked eye, you mean to say. But if you put it below the microscope, you will see a lot of ups and downs in the pipe wall. That is called roughness. That roughness causes the friction. So we can use it for single phase fluid. Again, in the fluid flow, there are very straightforward, simple flow patterns. A single phase fluid, either liquid or vapor or gas, or two phase. Sometimes you have a mixture of these two. So when you have two phase flow systems, the equations and methods become complex. The plant pipes are segments within the plant which are usually limited to 300 meters. Within the plant, pipes are all short pieces, not very big. Whereas pipelines are very long, they may run into kilometers. So the pipeline sizing, the criteria used for pipeline sizing is different. In this presentation, what we will see is the plant piping, process plant piping. And two criteria I told you in the line sizing, which are very important, is pressure drop and velocity criteria. And both are interrelated. Pressure drop is related to velocity. It's actually the square of velocity. Pressure drop is proportional to square of the velocity. If suppose your velocity is 3 meters per second, pressure drop will be 3 square, so 9, and some correlational constants. Okay. So accurate hydraulics pressure drop calculation depends on the physical properties, density and viscosity. It's very well known if it is a high density liquid or a high viscosity. High viscosity makes the flow a little difficult, and the flowability is a little difficult. You have to spend more energy. If you are pumping a high viscosity liquid through a pipe, you have to spend more energy than a low viscosity, let us say water. Okay, like that. Liquid density is given by rho, which is kilogram per meter cube, and relative density is nothing but compared to water at 150 degree, 15 degrees centigrade and 1 atmosphere. Okay. This is sometimes used in some correlations. So density of liquid at 15 degrees centigrade and 1 atmosphere divided by density of water at 15 degrees centigrade and 1 atmosphere. This is called the relative density. And density of water, we all know, at 15 degrees centigrade and 1 atmosphere is 999.1. Generally, we say 1000 kg per meter cube. So it is actually at 15 degrees centigrade and 1 atmospheric pressure is 999.1. Okay. Density doesn't have much bearing on pressure, but temperature definitely makes it. As the temperature increases, density will be reducing. API density in one of the earlier presentations we have seen is nothing but 141.5 divided by relative density, rho relative minus 131.5. So the same thing here, relative density is the density of the particular process fluid at 60 degree Fahrenheit divided by water density at 60 degree Fahrenheit. And these are all the basic terms. Process water, formation water, most crude oils and natural gas are categorized as Newtonian fluid, where the shear stress is directly proportional to the rate of shear. Maybe you may have to refresh slightly your fluid flow, fluid dynamics chapters. The viscosity of a Newtonian fluid does not change with the shear rate, and at low to medium pressures is only a function of temperature. Viscosity is a function of temperature. You simply remember, viscosity is a function of temperature. When you increase the temperature, viscosity reduces. Pressure effect on the liquid viscosity is almost nil. So how do we do the sizing of piping? Using these physical properties like density, viscosity, and the flowing parameter of the system, velocity. So Osborne Reynolds is the scientist who determined a number, dimensionless number. These are all called dimensionless numbers, because when you put all the parameters in the particular formula, the unit will cancel with each other. Finally, it will become a dimensionless number. So this scientist lived between 1842 and 1912. He was in the college, Owens College, Manchester, UK. Okay. What is the Reynolds number? You all know. This is the basic thing, formula you have to remember, is dV rho by mu, we say. Diameter of pipe into velocity multiplied by density of the liquid divided by viscosity of the liquid. So this is called the Reynolds number. This is an important parameter. This characterizes the fluid flow. So how do you calculate the velocity? I already told volumetric flow rate in meter cube per second divided by the cross-sectional area of the pipe. That becomes meter per second. So we have given just an example, 45 meter cube per hour, and per second divided by 3600 divided by the area. It's a 150 mm 6-inch pipe, 0.15 meter square. So it gives you 0.71 meter per second. So these are all very simple mathematics. Reynolds number you can now find out. 0.71 is the velocity, 0.15 the diameter, 1000 is the density in kilogram meter square, divided by viscosity 1.138. So you get a Reynolds number of 93,585. So the pipe roughness, how do you find the KS? It is called pipe roughness factor. In some texts, it may be quoted as E. Commercial steel pipe would generally be taken as 0.4045 meters. It has a unit, and the KS is not a dimensionless factor. It is a dimensional number. It is measured as meters, 0.00045. So from the relative, this is available in the literature. Don't worry, how to calculate and all. For different pipe materials, we have tables available which will list the roughness parameter for the particular type of material. Okay, stainless steel, carbon steel, brass, all those things we will have. So from this relative roughness, we can find out what is the, for that particular pipe. Relative pipe roughness is nothing but your pipe roughness divided by the diameter, pipe bore, okay, ID, internal diameter of the pipe. The friction factor can now be determined from the Moody chart. Moody also is one of the scientists who has developed the fluid flow characteristics. So frictional head loss is calculated using the Darcy equation we have already seen. So Moody's chart is nothing but Reynolds number in the x-axis versus the coefficient of friction. Okay. And then there are a lot of curves you can see. All these curves are relative roughness. So Ks by D. So once you calculate the Reynolds number, for a given Reynolds number, you can find out the coefficient of friction. For example, if it is your 10 power 5 means it gets you something like 0.0046, I would say. Okay. So just to understand, these charts are available in your textbooks also. So from example 1, we have determined the velocity, etc. Relative roughness is for a commercial steel pipe, Ks is 0.000045, diameter is 0.15 meter, relative roughness is 0.0003, and Reynolds number we have already calculated is 93,585. Friction factor is 0.005. So this is how we determine the friction factor from the Moody chart. The pressure difference between 2 points can be done by the Darcy's equation. Here again we use the formula head loss. HF is head loss due to friction. 4FL U square is velocity square divided by 2GD. It is a momentum thing happening. So you have the gravitational constant and the diameter. So F is the frictional factor which we have just now determined using the Reynolds number and Moody's chart. L is the length in meter and the velocity in meters per second, that is U. G is the gravitational constant, it is 9.81 meter per second square. D is the pipe diameter. So using this formula you can find out the frictional loss. Darcy equation is a length term which is calculated considering straight length and the equivalent length. There are, when you come to the length of the piping, there are the straight pipe and the equivalent length. So in the diagram, we have seen straight pipes and they are connected by fittings. We are connecting them with elbow or bend or T or reducer, expander. These are all called pipe fittings. So straight length you can measure and take. And what about the effect of these fittings? The fittings will have more pressure drop because there is a direction change. If it is a elbow, the liquid takes a directional change, and it has to spend more energy to take that one. So we calculate, we convert that fittings into straight equivalent length. So if you say it is a size of the fitting and type of fitting. Suppose I say 6-inch elbow, 90-degree elbow, means it has a equivalent length. It may be, it is expressed in terms of diameter. So a 6-inch equivalent length for 6-inch 90-degree elbow may be 10D. Means that one piece of fitting is equivalent to 10 times the diameter. That is called equivalent. Suppose your 6-inch means one fitting elbow is equal to 60 inches. So we have to convert all the fittings into equivalent lengths and then add this along with the straight line. That will give you the total length, which is the term used in the formula. I have already expressed. And walls also we have similarly the equivalent length factor. If you heard of this API, American Petroleum Institute standards, there is API 14E. API 14E has a table which tabulates the various types of fittings, and size wise it tabulates and it tells you what is the equivalent length for each type of fitting. So this is a table I am just showing you, type of wall or fitting. Ball wall means it is equivalent to 3 diameter. You have to take 3 times the diameter as the equivalent length. Gate wall is 13D. Okay. Walls fully open globe wall is 340 diameter. You can see the enormous. That means the pressure drop through this device, this globe wall, is very high because it's a very restricted flow path inside the wall. Okay. Check wall, swing type, different types. Fittings, elbow, you see, 90-degree elbow, okay, is 20D. 45-degree elbow is 16D. Similarly, bend, long radius bend, short radius bends. So you can see different types and sizes of fittings will have the equivalent length expressed in terms of the diameter into a particular number. Okay. Nozzles 32D. Okay. 32 times the diameter of the nozzle. So similarly, maximum velocity, what we can allow in pump section, discharge, etc. For liquids, pump section, we go up to 1 meter per second. 0.6 we have given. And pressure drop is for 0.01 to 0.05 bar per 100 meter length. Okay, so if you know the total length, you can find out the exact pressure loss. Okay. Maximum we can go up to 0.09. So these are all the guiding tables, pump section. Pump discharge, we can go up to 1.5 to 4.5 meters per second. Okay, up to certain size range. If you have pipe size greater than 20 inch, is a big pipe. Okay, so we can go up to a maximum of 6 meters per second. So normally when we size the piping for a new plant, we keep something like 3 to 3.5 meters per second. Okay. When we revamp a plant, when we work on an existing plant where we want to do some modifications, we want to increase the plant capacity, etc., then we allow a higher velocity. Okay. So we don't want to change the pipe just for slight increase in the velocity. So these tables give you for different scenarios, different types of operations, what is the velocity allowed. Okay. Vapor flow, now liquid flow we have seen now. The vapor flow in the piping, we have two types of categories. One is incompressible flow and compressible flow. You all know vapors and gases are compressible fluids. So you can compress them and make them smaller volume with high pressure. So, whereas liquids are incompressible. We can pump only, but you cannot compress a liquid into a smaller volume. So, but vapor, when gases flow in the pipe also, they have certain characteristics. They behave like liquid, that is incompressible flow up to certain limits of velocity. Beyond certain velocity, they become compressible. So the correct line sizing criteria must be selected depending upon the type of vapor flow. When the incompressible vapor flow happens, the kinetic energy losses caused by the acceleration of the fluid are negligible. This is the case when both the following criteria are met. Vapor velocity is less than 60 meters per second. Total pressure drop is less than 10% of the initial pressure. In the first slide, I have shown you the fluid traveling from point 1 to point 2. So that is the distance, okay? So point 1, we have pressure P1, point 2, we have P2. If P2 is only 10% of the initial pressure, suppose at point 1, pressure P1 is, let us say, 5 bar, and point 2, after traveling some distance, if the pressure loss is less than 10%, that is less than 10% of 5 bar is 0.5 bar. If it is less than 0.5 bar, it will be incompressible flow. It behaves more or less like a liquid. So your equations given above will be useful. Normal process utility vapor flows fall in this category. The lines are sized for isothermal incompressible flow. Isothermal, you mean there is no change in temperature. And vapor services excluding flare, vent, PSV fall in isothermal compressible flow. And most of the cases we restrict the velocity of vapor or gas in the range of 15 to 30 meters per second. So mostly we reach something like incompressible flow only. So you can easily remember. So the normal velocity criteria we use for gases and vapors in the range of 15 to 30 meters per second, and the 60 meters per second limit given was sometimes we reach in the vacuum service. Usually in the vacuum conditions, gas velocities are high. Higher velocities are allowed. Then one more criteria we use is rho into velocity square, density into velocity square. So it is governed by consideration of vibration and forces on piping supports. The rho v cubed, the density into velocity cube criteria are governed by consideration of noise levels. So when a fluid flows in a pipe with certain force, we can see the pipe may vibrate. You can see the vibration in the pipe. That vibration is a function of density into velocity square, density of the fluid. Also, sometimes it may create some noise. You can hear the noise when the fluid flows inside the pipe. Still, you will hear some noise. Sitting near the pipe, you can hear the noise. That noise is a function of density into velocity to the power 3, rho v cube. So these are all the factors which we use when we design the piping, and we give these numbers to the piping engineer. So he will do some analysis and they will provide the pipe supports. Pipes need support. They run meters and meters. You need to support. Even in the household plumbing, you might have seen the plumber puts clips on the wall. When the pipe runs along the wall, he puts that, say, every 3 meters, he puts a clamp, because to arrest the vibration or movement of the pipe. So these two criteria are used to secure the pipes during operation. So here gases, we have the rho v square. Okay, gases depending upon the pressure less than 20 bar gauge pressure means we allow up to 6,000 rho into v square, kilogram per meter per second square. Okay. And as you increase the pressure 20 to 50 bar, we can go up to 7,500. 50 to 80 bar, we can go up to 10,000. Greater than 80 bar operating pressure, 15,000. This is the rho v square allowed. This is the sizing criteria, you can say. Okay, you can fix this sizing criteria and find out the velocity. From the velocity and the volumetric flow rate, you can find out the size of the pipe. Column gas outlet. compressor suction, compressor discharge. So these are all the criteria used. Using these numbers, rho v square numbers, you can find out the size of the pipe. Compressible happens when the pressure drop exceeds 40% of the upstream pressure. We said if it is 0.1 to 0.2, if the pressure drop experienced by the gas is less than 10% of the starting pressure, it is incompressible and it is governed by the criteria given above. If it is more than 40%, it becomes a compressible. So this happens when you have a great reduction in pressure, like the relief valves, blow down valves. So there is a great reduction of pressure from the upstream to downstream of the valves. So those places, downstreams, you will see a compressible vapor flow. So adiabatic condition is usually considered for short, well-insulated pipelines, while in long pipelines, it approaches the isothermal condition. So in general, isothermal condition pressure drop is greater than or equal to adiabatic pressure drop. If pressure drop in pipe segment exceeds 10% of this we have seen. Pipe shall be divided into segments to keep pressure drop in each segment below 10% of the upstream pressure. This is usually done using a suitable computer program. To find out these progressive pressure drop along the flow path, we use certain computer programs, computational fluid dynamics. It is called CFD, computational fluid dynamics. We will not talk about those software here. And two-phase pressure drop correlations are available in literature. For piping within plant boundaries, two-phase lines are sharp. Pressure drop based on average density is generally adequate. If you have vapor and liquid mixture flowing in the piping, you take the average density. What is average density? Density is mass by volume, correct? So you have liquid, you know the mass of liquid and you know the density of liquid. The mass by density gives you volume. Similarly for gas, you know the mass rate and density, find out the volume. Add these two volumes is the total volume. You know the total mass, liquid plus vapor, divided by volume, average volume, then it gives you average density. You can use this density for pressure drop calculations. So there are some correlations developed by scientists like Bex and Brill, may be more useful. And flow regime, we say when there is a mixed flow, it can flow in different patterns. That is called flow regime. The interaction of the liquid and vapor phases is complex, and depending on the ratio, the piping size and layout. So flow regime is still a complex one. So a complete understanding is still going on, but we have correlations to find out what is the flow regime. Different patterns are there in the flow regimes. Emulsions may form, or the pressure drop may be higher than expected. Where phase change is expected, unstable flow regimes may result, etc. A lot of complicated things can happen when there is a mixed flow in the pipe. Flow regime depends on the flow rate and physical properties of gas and liquid phases, as well as the pipe characteristics like diameter, length, whether the pipe is running in a horizontal direction or vertical direction. These parameters will decide the flow regime. We have different types. I just give some names. One is called mist flow. You all know mist. In winter mornings, you will see mist in the outside. Mist is nothing but distribution of liquid in small particles in the air. That is called mist. Same thing can happen inside the pipe where liquid is distributed like small droplets in the gas phase. Stratified flow means you have one layer of liquid, above that you have a gas layer. So they segregate themselves within the pipe. So fluid, if it is horizontal pipe, you will see the liquid flowing in the bottom of the pipe and above which the gas flows. That is stratified. They segregate themselves. Slug flow means in gas pipelines, the liquid may form a slug. So there will be a gas pocket and then followed by liquid like that. So you can have gas slugs or liquid slugs depending upon the proportion. If you have more vapor, less liquid, you may find slugs of liquid. You can see, interestingly, if you note down in the house, suppose you open the tap, sometimes you hear a lot of noise and then some gas comes. Suppose the line is empty, when you open, what happens? The air in the line is first removed, correct? It is pushed by the liquid which is coming from the tank above. So the head in the tank drives the flow. So if there is a air entrapped inside the pipe, when you open the tap, you will see a lot of noise and then blood, some gas comes out and then you will find pockets of liquid and it takes some time to get the clear liquid flow. This is called slug. So how do you find which flow regime? So don't worry about this flow regime and all. You just have an understanding, because these flow regime and all will be handled by certain specific software. Okay. We find out the flow regime using a Froude number. It's again a dimensionless number developed by the scientist Froude. So you calculate the gas Froude number, which is nothing but Froude number gas is velocity of gas multiplied by under root density of gas by density of liquid minus density of gas into gravitational constant and diameter. Okay. Similarly, for liquid, you can calculate the Froude number as Froude number liquid, V liquid, the same formula, rho L instead of G, here rho L minus rho G, gravitational constant and D. So there is a chart, a Froude number chart. Okay, this is the Froude number chart, two-phase flow regime map for a horizontal flow. Okay. So liquid Froude number in the vertical, gas Froude number in the x-axis, horizontal. So you can find out gas Froude number and liquid Froude number when you meet these two. Okay, you have, let us say, your Froude number gas is 1. Okay, and your Froude number liquid is 1 power 001. So that is, you travel like this and then here somewhere you are in the intermittent plug or slug flow. Okay, so this is how the flow regime is determined. You have stratified smooth flow, stratified wavy flow, annular or dispersed flow. Annular means you have a outer circle of liquid, inside pore is gas. Intermittent plug flow or slug flow and bubble flow, etc. So just to have an understanding of this. Okay, so this completes the line sizing part. Then we go into the line list. So after doing all calculations, determining the sizes of various piping in different parts of the plant, we have to list those things, and then that line list is given to piping. So that will help them in making the arrangement drawings, general arrangement drawings, and then the isometrics. Somebody asked about isometrics in the last session. Isometrics is the, see, isometry, you can see the sketch I showed you, 3 tanks interconnected by piping. You can have a 3D view, correct? That is isometrics. 3D view is the isometry. So now we will see about a line list. I will quickly run through. Line list is, the name implies that it is a listing of all the lines with its parameters. Each line has its parameter. Okay. Understand the information contained in the line list and how to populate. Populate means how to prepare, fill the line list. Line list as a standard format. So line list is nothing but a document prepared by process engineers. It will list all the piping involved in the plant as indicated in the P&IDs. P&ID, you have seen every line is numbered with a lot of attributes. The line number tells you the size of the line, the material used for that pipe, pressure rating for that pipe, and whether it is insulated or not. All those details will come. Okay, operating pressure, temperature, design pressure, temperature, and test conditions, all those things will come in the line. So in the line list, we fill all this information. So why we need it means piping engineers require line list data in order to design the piping system. They need this data. Line by line, they want the data. The data entered in the line list is data used to design and procure and construct the piping. So based on your line list, they will estimate the quantity of piping required in the plant. Then they make a piping material requirement. We call it as MTO, material takeoff. And then they make the general arrangement drawings, isometrics, etc. When we issue it, immediately after completing the P&ID. So once we come to the issue for approval, we have seen various stages in P&ID, interdiscipline review, IDC, followed by the client review, that is IFR. So once client comments have come, we have incorporated, then you issue it for this one. Line list can be taken from the client approved P&IDs. So format is subject to change. The different formats are there. Clients will have certain formats. Sometimes the project will determine the type of format required. But there are basic parameters which are listed. Okay, so we have to have a clear understanding from client and the project what format should be used. Okay, and this will also be in line with your legend P&IDs which we have seen earlier. So this diagram may not be very clear, so don't worry. But the line list has so many columns. Okay, even I may not be able to read here. This is one sample line list where, very importantly, I would say you should put the line number and in which P&ID that line comes, and where it starts and where it ends, and then what is the line number, and then you list the material of the line, operating pressure, temperature, design pressure, temperature, and what is that fluid flowing inside, whether it is liquid or vapor or gas, and then you give the properties also. Okay, density of, if it is a liquid line, say liquid density, etc. It can be elaborate. We can put all the details about that particular line in this, and then also you will say what is the test condition, whether it is hydro tested line or pneumatic tested line. Then what is the testing medium, that is type of testing, and what is the medium used for testing. Finally, you will have some blank columns. These are called remarks, where you can write specific requirements. You can say it's a sloping line, no pocket line, etc. Those things you can write. So now I will show you. That diagram may not be very clear. Now you can see the line list. Piping related data we put. It's the area code. This comes in this particular area of the plant. Okay, and then we put the size of the pipe, 24 inch, 18 inch or 2 inch. Service code AG means associated gas. Unit code, the particular piping comes in unit number 11 of the plant. Sequence number, you give a number to the line, that is 119. This is another example. Material is 9L6N. This we will see what is 9L6N. So area code we understand, particular area of the plant. Okay, central processing facility, utilities, tank farms, etc. Then size of the pipe, typically represented in inches. This is always the convention. We don't put millimeter, meter, etc. It is always given in inches. Service code, what is the service? AG, acid gas, HC, hydrocarbon. Okay, like that we put the service code. Unit code is plant may be separated to different units. Within the acid gas plant, you may have absorption, dehydration, dew pointing. So these are all the units. So these are all to identify where the pipe is exactly located. Sequence code, it is number is sequentially done from starting of the plant to end of the plant. Last one is material class. So that let us see in next slide. Material class is 9L6N. First item is indicates the pound rating of the line, that is pressure rating. 9 means 900 pound rating. Okay, this I am trying to get a table. What is 150 rating? The 150 I can tell you, it is up to 19 kilogram per centimeter square pressure is called 150 rating. Similarly, we have 300, 600, 900, 1000. As the pressure increases, each rating is a range. So 0 to 19 kg per centimeter square is 150 rating. That is the lowest rating. So then you have 300, 600, 900. I will try to get you the table next time. So as the pound rating increases, you can say the pipe can withstand a higher design temperature and design pressure. Means you, the conditions of the pipe will be, it will be thicker pipe. As you go up in the rating, it will be a thicker pipe to withstand the higher pressure and temperature conditions. Second item is L. What is L? L is the actual material. In this case, L is low temperature carbon steel. If it is C, it will be carbon steel. If it is stainless steel, we put S. Okay, this is the material code. Third item is 6, indicates the corrosion allowance. Here 6 means 6 millimeter corrosion allowance. What do you mean by corrosion allowance? The material, we have seen material selection diagram. There is a department called material department. They determine the corrosive nature of the fluid. Once we give the fluid properties, they will define what is the type of corrosion that may happen. So they add a corrosion allowance. So what do you mean by corrosion allowance? Suppose you calculate a pipe thickness based on the pressure and temperature inside. Let us say you get a wall thickness of 10 mm, let us say. So that is a bare pipe. Okay. But if there is a corrosive fluid flowing inside the pipe, it keeps corroding and eroding the wall. Wall thickness will become less and less over a period of time. So to take care of that, we add this corrosion allowance. If your calculated thickness is 10 mm and corrosion allowance is 6, you add these two, you get 16 mm. So you will have to use a pipe of 16 mm thickness. What is the meaning? The corrosion department says 6 mm corrosion allowance is required for a plant life of, let us say, 25 years. The meaning is today you put a pipe with 16 mm thickness and it is put into service, the plant is operating. After 25 years, it is supposed to be all the corrosion allowance is eaten away. So if you measure the wall thickness of the pipe after 25 years, you will be left with the base thickness, 10 mm. So that is the idea of corrosion allowance. So fourth item N is the class differentiator. That means NACE, N-A-C-E. NACE means the service is having sour type of fluids, that is hydrogen sulfide, carbon dioxide, these are all there. So it is a sour service line. So it is subject to NACE requirements, National Association of Corrosion Engineers. So we put that N. If it is a flare line, we may put F. Okay. It is a further identifier for the class. So pipeline data, from to I told you, this starts from this point to the other point, this equipment to other equipment. Then P&ID number. What is the phase of the fluid? Whether it is, it can be vapor or liquid or a mixture of vapor liquid. We call, if it is vapor, we put V. Okay. And then density. If it is a gas, 84 kilogram per meter cube. The from is the source equipment, to is the destination. It is connecting two points, point 1 and point 2. So from 2 is the one. P&ID number, which P&ID this line is appearing. Phase, what is the condition of the fluid flowing inside, vapor, liquid or mixed phase, and density of the fluid flowing in. If it is a mixed phase, density of both phases you have to give. If suppose you have vapor and liquid, you have to give density of vapor as well as density of liquid. So similarly, design conditions, design pressure, maximum design pressure, that is 105 bar gauge. Minimum is full vacuum. Maybe it will have steam service or some condensing service. So it may full vacuum. Okay, so it is to be designed for, on the positive side 105 bar gauge, on the negative side full vacuum. Similarly, temperature, maximum design temperature 80, minus 45 is when there is some depressurization done. Okay. Operating, you can put the actual operating pressure and temperature. Operating temperature may be over a wide range, 45, 42, 40. And alternative, in some cases, if the equipment or the plant is to be run for two different conditions, two different operating cases, then you can put the alternative pressure and temperature. So design pressure, design temperature, we have already seen. Design pressure is operating pressure plus some margin. Okay. We can see operating pressure in this case is 95.2. Design pressure is 105. Okay. Maximum operating temperature is 45 and design temperature is 80. There is a margin added depending upon the service conditions. Operating pressure temperatures you know very well. Alternate is when there is a different type of cases, operating cases, or you use a different fluid in the plant, or when there is some upset happening in the plant, upset conditions, there may be a different kind of conditions, pressure and temperature. That is alternative. It may not be there in all the cases. So these are all some specific cases. Then we have talked about test medium. Here H means hydrostatic test, and you can see pressure, test pressure is 160. Okay. You have seen 105 is the design pressure, and test pressure is 160. Okay. So about 60 bar more, 55 bar more. That means 1.5 times. Okay. Electrical tracing. It means this particular line carries some fluid which you have to maintain an operating temperature all the time. When there is winter, it has to be maintained. So we have electrical tracing. The pipe is wound by electrical tracers, and it will be continuously heated by electrical heating. So it is called ET, electrical tracing. If you use steam for heating, it is called steam tracing. Okay. Then insulation type we have given. Insulation thickness is 30 millimeter insulation thick on the pipe, and degree centigrade is 25 outside temperature. Paint class, this is given by piping engineer. L4. Somebody is waiting. Prem, you can allow them in. Okay. Then we put remarks, note 1, hold 1, etc. Revision. Every document developed by process or any engineering discipline for that matter will undergo a number of revision. Changes keep happening. So this is revision D1. So we have seen the parameters. So this we have to prepare for all the pipes in the plant. So you can see it will be a voluminous thing. Just I have shown a bunch of papers here. Like that, the line list runs into a number of pages. And the line is indicated like here, you see 18-inch pipe, acid gas. This is line number. This is the material class. And there is electrical tracing, ET, 25 mm thickness of insulation. You can see chain dotted line. Okay. I don't know whether you can see here. Chain dotted EE, you can see E continuously. That means electrical tracing. Nowadays, there is a smart plant software is there which develops the P&IDs in a smart format, which will have all the details input into the P&ID itself. So whatever conditions we have seen, line attributes, equipment attributes, valve attributes, we put all the data inside the P&ID, and it is called the smart plant P&ID. It takes time to develop smart plant P&ID than a simple AutoCAD drawing, but it is very useful. Once you do the complete P&ID in the smart plant platform, you can easily extract line list, equipment list, valve list, etc. You just give one command, it will list all the lines, okay, with all the attributes. That is very comfortable. Nowadays, most companies do this smart plant P&ID because initial development takes time, but it is very useful when you want to extract line list, when you want to extract equipment list. You can extract valve list, you can extract instrument list, etc. So just to have it in mind, smart plant P&ID. And further fluid categories we have already seen, operating conditions we have seen. Where do you get the fluid conditions? From the heat and material balance. Okay, it gives you the kind of fluid running in that pipe. What is the conditions, physical condition, whether it is vapor, gas, or liquid, or mixture of vapor and liquid, density of the phases, then operating pressure and operating temperature. All those things are obtained from the heat and material balance. So design conditions, we have to get it from the safeguarding diagram, or sometimes we make design pressure and design temperature diagram, which I forgot to tell you. The same PFD, we can also make one more diagram. From PFD, we made a PSFD, process safety flow diagram, material selection diagram, etc. One more drawing we can make is DPDT, design pressure, design temperature diagram. That is, take the PFD and put all the design pressure, temperature on each and every line and each and every equipment. Then it is called DPDT diagram. Some companies make a DPDT diagram. Example, Foster Wheeler, usually they make DPDT diagram for all their projects. Okay. Utility flare drain lines have project specific design conditions. So design temperature is the material temperature representing the most severe condition. So we see what is the worst condition that can happen in the plant, and that temperature you take it as design temperature. Usually it is 10-15 degrees more than operating temperature. In some cases, when you use steam or any hot oil, you have to see what is the coincidental pressure and temperature. So that is the one we have to take. Always the worst conditions, the maximum conditions have to be considered. Similarly for the design pressure also. The most severe condition that may happen in the particular equipment or particular unit. So design pressure of the connected equipment also we have to see. Similarly, when you design temperature, when you see the pipe connects to certain equipment, okay? See the conditions of the equipment also. If the condition of the equipment is severe, then use that same temperature for the connecting pipe also. Similarly for the pressure. And pumps, etc., the design pressure will be, for centrifugal pump, you can, when you run the pump, you can close the outlet valve of the centrifugal pump. So once you close the outlet valve, the pump keeps running. It will develop the maximum head or maximum discharge pressure, that is called the shut-off head. That is, when you shut off the outlet, it develops the maximum pressure. That is called the shut-off pressure. So design pressure for pump discharge line will be shut-off pressure. Okay. So we have to see the various operating scenarios for the equipment, connected equipment. Then you have to incorporate those conditions in the connecting piping. Test medium, test pressure, we have already seen how it is done. Okay. Various sources exist for obtaining data to populate the line list. We have already seen heat and material balance is one thing, design pressure temperature charts are one thing. And a connected equipment condition, just now I have told, if you have different conditions for vessels. You can see here one vessel is operating at design pressure of 5 bar gauge. The connected equipment is 15 bar gauge. So where you have to use, there is a valve here, okay? There is a valve in between these two systems, okay? This is supplying to the pump, but pump is discharging at a 15 bar gauge. So first isolation valve to suction should be the 15 bar gauge pressure. So, okay, up to this can be a 5 bar. So pump discharge is 15 bar, so entire discharge line and part of the suction line up to the valve and then to the next vessel, all are 15 bar gauge. So you can see how the operating conditions of the equipment determine the design pressure, design temperature. So through PSVs, you see 130 bar is the pressure in this vessel. So it will go up to this first isolation valve. Then we have a relief valve set at 105 bar. So when this pressure reaches 105, it will open and release. So after the safety valve, you can see the design pressure is 105 bar for the line and equipment. Okay, this vessel is 130 bar. So these are all the scenarios where your line conditions are dictated by the operating scenarios of the connected equipment. So header design, how do you, header means a number of lines will come and join a header. So there is a pump which is discharging into this header. you have a vessel from which some fluid is flowing. So temperature, let us say this is 10 bar gauge and 80 degrees centigrade. A pump is pumping at 15 bar gauge and 100 degrees centigrade. This vessel is design pressure of 4 bar gauge, but temperature is 150. Okay, you can see different conditions. So up to the valve, the particular equipment conditions will prevail. After that, it will increase. See the worst of these conditions, temperature 150 is the maximum here, and pump is pumping at 15 bar gauge. So these two are the highest possible condition. So the entire header will be having design pressure of 15 bar and design temperature of 150 degrees centigrade. So this is how we determine the line design conditions. This we have seen 105 bar, 130 bar. We have just now seen similar case here. And flare lines, the flares are operating at a very low pressure conditions. So we have to put the flare conditions up to the valve. Afterwards, it will be reduced. So we have 105 bar, 80 degree, minus 10 degree. This is 105 bar up to this point, and design temperature is 100 and up to minus 100. So these are all the conditions happening in the plant depending upon the operating conditions of the plant. Full vacuum is, I told, only when you have steam or any kind of condensing services. Anything that condenses in a vessel or line, the volume greatly reduces, you know, okay. Vapor may be, let us say, 100 meter cube of vapor. When it condenses, it may become 10 meter cube. That is, there is 1:10 reduction in volume. So it pulls vacuum. So when such operating scenario is seen in the equipment, you have to design the equipment for full vacuum. Also, the connected lines should also be designed for full vacuum. One positive pressure will be there, and also the full vacuum, negative conditions. Nodes and holes, we always write like P and IDs on the right hand side column, you write nodes. Hold is some information which is not available. So we put a nodes there and we list the holes. Holes will be removed when the project matures, when you get more and more information from other disciplines, from vendors, from client, hold will be removed. So here also in the line list also, you will have last 2-3 columns I showed you is used for notes and holds and remarks for any special conditions. Okay. So some of them are, say for example, line to be designed for slug flow. That means this line may see slugs, and then you have to give, slugs are there, you have to give the slug type of slug, number of slugs, etc. It may create some vibrations. You have to give rho v square, we have seen, isn't it? Vibration is a function of velocity square into density, and also noise is a function of density into velocity cube. So those things we have to calculate. EDG means electrically traced lines should always have electricity supply. When there is a power shutdown, how do you ensure power supply? You put in the note EDG is provided, means emergency diesel generator is provided as a power backup. So the heat tracing, electrical tracing keeps getting the supply. Okay. This is something like UPS you have at home, correct? When the power goes up, UPS takes care, but UPS will not address all the loads. But at least you will have fans and lights running. You cannot run the air conditioner. Similarly, in the plants also, we have emergency diesel generator when there is a power failure. And when we make the electrical load list, we mentioned that the electrical tracing should have a power backup by EDG. Okay, important critical power requirements, we put it in the load list, which the electrical department will size the emergency diesel generator for those emergency loads. Okay. Holes indicate that something is still not available or parameters. We are pending for some information from the other parties. So, but slowly when you reach the IFC case issued for clearance P and IDs, all the holes must have been removed. Okay. Sometimes line size, itself can be held in flow rates, or hydraulics is not done. Or you are waiting for some computational fluid dynamics is done. So computational fluid dynamics is done by a specialist. So till we get the recommendation from CFD analysis, you may not be able to confirm the line size. So some people are coming and joining now. It is too late. It's almost over. Design pressure, anything information which is not readily available, you can put a hold and try to get the data from the concerned department or vendor or client. Okay. How to make the line list? General tips: ensure operating conditions do not exceed design conditions. Ensure that design conditions do not exceed the pipe spec. Pipe specification gives 900 pound rating. It gives piping specification gives you the maximum value. So design condition should be within that. There is an important document I told you in one of the presentations, piping material specification, which is prepared by piping department. That also lists design maximum design pressure and design temperature that can be applied on the particular piping for a particular service. So you have to see that your design conditions do not exceed the piping specification. Ensure that you don't grossly oversize the pipes. 900 pound rating with a design pressure of 10 bar gauge, you should not put 900 pound rating. 10 bar gauge is coming within the 150 pound rating. Like that, you have to see these anomalies. Okay. Keep the reference documents for all the line list work, your hydraulic calculations and various heat and material balance. All those documents are the reference documents for line list. You keep them all in separate folders, and you should have access to these anytime. Okay. When you have any doubt, you always ask questions to your seniors. This is the general guideline for not only for line list, for any document you are asked to generate. Better understanding should be there. If you have any doubts, you always ask your seniors, your lead engineers. Okay, don't shy away or don't be hesitating to ask any questions. The more questions you ask, at least as a fresh engineer or engineer with 1 or 2 years experience, it's better to have a clarity that is the time you learn the subject. So don't hesitate or shy off to ask questions. Okay. Line list, don't underestimate. It's a dull task. It is a laborious task, but once you are able to make a line list yourself, you will learn a lot of things, because line list is connected with heat and mass balance, hydraulic calculations, piping material specification. So many documents are used as reference. So you will get to know about all these types of documents. You will have a full understanding of the piping system. So it's not a dull task, but it is a very good opportunity to learn about all the related documents. So I think we have come to a conclusion. And now it is open to questions. Somebody has come at the last minute.
No, sir. I think there are a few disconnections there. Yeah. That is why they're coming back. So they are attending.
Please tell them, maybe they can, where they can see it in the YouTube or what?
Yes, sir. Yes, sir. They can very well see it on YouTube.
So people who have lost their internet connection, or for any reason connectivity is lost, don't worry. You can always see in the YouTube. Okay, whatever you missed in the presentation, you can always see that.
Yes, sir. So we'll be sending the link also.
Now we will answer the questions.
Yes, sir. The first question is, sir, is a pipe and a tube technically same or different?
No, pipe is usually wall thickness is more, and pipe always is given by a diameter called nominal bore, NB. Okay. For pipes up to 12-inch size, the diameter is more than, if I say 6-inch pipe, its outer diameter is more than 6 inch. After 12 inch and above, if I say 12-inch pipe, the outer diameter of the pipe is exactly 12 inch, 14 inch, 16 inch, 20 inch. 20 inch means it's 508 millimeter. That is the outside diameter of the pipe. Below 12 inch, it is slightly higher value. There is a table which lists the pipe sizes, nominal bore, and what is the outside diameter. In pipes, it is always outside diameter. Whereas tubes, it is inside diameter. Tubings are normally used for small bore pipes, small diameter, and also they are used in the very delicate services. Like in instrumentation, you will see all tubing. The instrument air connection to the control valve. Okay, lot of small bore piping used in instrumentation, and they are all the tubes. Tubes are for a particular service, and they are usually small diameter in size. So pipe is always for the process services, and pipe diameter always relates to the outside diameter of the pipe, whereas tube, it is usually ID, inner diameter of the pipe. Yes.
Okay,
for tubing, I think there is some British standards are there. Tubing is British standards, whereas for pipes we have American National Standards Institution, ANSI, NC is there. That is our piping standard. Yes, next question.
So the next question is, what are the methods done to reduce form friction? Form friction.
I didn't get that. What is that, pump section or pipe section?
Form, sir, form.
What is a form used for?
Friction. What are the methods are done to reduce form friction?
Oh, friction, you can use smoother pipes. Some materials will have smooth inner side. So you have to go for such materials. And this roughness factor and all I told you, it is all available in the literature. You have for different materials. Maybe you can see stainless steel, okay, normal carbon steel piping. The pipes we use in even household plumbing, you use GI pipes, correct? Galvanized pipes. The roughness is physically seen. If you touch with your finger, you can see the roughness of the pipe inside. The same thing, you take a stainless steel pipe, you will see it is very smooth. So the roughness can be selected. If you want a very smooth pipe, you go for stainless steel, which is costly, expensive, but it gives a comparatively smooth surface compared to carbon steel pipe, etc. If you use a cement pipe, let us say, cement pipes are used for drainage and all. So they will be more rough. Cement surface, you know very well. Okay. So roughness, you can manage with the type of material.
Okay, sir. Okay, sir. The next question is, what is the sizing criteria for non-Newtonian fluids?
Non-Newtonian fluids.
It's a sizing criteria.
Non-Newtonian fluid, we have the charts we have used. Non-Newtonian, and the slide I have shown you. It's not a linear one. Newtonian is linear. Shear stress to shear is a straight line. This one, straight line relationship. But non-Newtonian, it is, you have seen the charts in the textbooks also. You have Newtonian, non-Newtonian fluid characteristics you have seen. The correlations will be differing. I think I have mentioned in the text, but I have not given you any equation. Maybe equations you may have to refer to the textbooks. Newtonian, non-Newtonian. Okay, so I will make a note of it. Non-Newtonian transition. Okay. Somewhere in the presentation, I think I mentioned. Let me see. Well. Equivalent length. Friction factor can now be determined. Pipe roughness, Reynolds number. Friction factor depends on the Reynolds number. Newtonian process water formation where the shear stress is directly proportional to the rate of shear. That is Newtonian. The viscosity of Newtonian fluid does not change with the shear rate at low to medium pressures. The functionality is usually depicted. I think I have not talked much about the non-Newtonian fluids. Pipe sizing. So I think non-Newtonian is not mentioned here. It talks about the Newtonian. Most of the process fluids like process water, formation water, most crude oils and natural gas are Newtonian fluids. So that is one advantage. But non-Newtonian, you are right. I think you may have to refer to the textbooks, what correlations to be used. Okay. Yes, Prem.
Okay, so the next question is, sir, can we put a pipe on another pipe? Will the top pipe exert high load to bend the lower pipe?
This I don't understand. This is making the pipe or what?
I'm not sure, sir. It is an anonymous question, so I don't know who asked.
One above the other, there is no problem. There are pipes running. If you go to any plant, you will see number of pipes running one above the other. They will be properly secured and supported. And there will be a pipe rack, it is called. Number of pipes will be running in the horizontal supports. It's like a corridor, pipeline corridor, pipe corridor. So they can be put one above the other. There is no problem, provided they have their own insulation and other requirements. Keep some distance between the two pipes. That is done. I hope he is not asking about double pipe, pipe inside another pipe. So if that is the pipe arranged in sequence or one above the other, all piping engineers will decide how to run the pipes depending upon the connectivity in the piping between two equipments, elevations, etc. will define. It is possible to run pipes one above the other. So
Okay.
piping will decide and they will provide proper supports for that. Yeah. Okay, next one.
The next question is, sir, please can you explain more about adiabatic pressure drop?
Adiabatic is the heat content is not changing, correct? Isothermal happens at a constant temperature. And by default, the isothermal operations usually have higher efficiency, operating efficiency, whereas adiabatic it may be less. Adiabatic contains the energy within it, and that leads to increase in temperature. That is what is adiabatic. So in compression, you will have isothermal compression, adiabatic compression, etc. Means when you compress the gas, the pressure increases, at the same time temperature also increases. Physically, you understand gas molecules are spaced apart. Okay, when you compress, what happens? The molecules are brought closer. So when the molecules come closer, the collision is more, the energy dissipation is more. That is why when you compress the gas, it becomes heated up, and then that is why when we have compressors, we always cool the gas from the discharge of the compressor to bring it back to the suction temperature. So when it goes through number of stages in the compressor, we do interstage cooling to bring it almost like isothermal compression. Between every stage, we cool the gas to the suction temperature of the first stage. So it is almost like you are trying to make it isothermal. So because isothermal, the energy dissipation is less and it's more efficient because of its inherent nature. Yes, next question.
So the next question is, during initial design phase, how do we get exact quantity of T's, bends, etc. for pressure drop calculation, or is it done on some assumption?
Maybe next session we will talk about pumps, hydraulics, etc. It is from the approximately it is estimated. Process engineers who have experience, they have some guidance. So they from the P&ID look at the P&ID and try to get approximate quantities, whether how the pipe is connected between equipment, whether there is elevation changes and all. So they approximately put, okay, consider 5 elbows, 2 T's, etc. When there is a branching in the pipe, then they consider T's, etc. So it's a little tricky subject, and it needs some experience. So estimation of number of fittings. That's why what happens after actual piping is done, okay, we will exactly have the fittings count. Then at that time, again, we redo the hydraulics, line hydraulics we do again after piping completes the piping design array layouts and then isometrics, etc. Based on final isometrics, we will exactly know the number of fittings, type of fittings. You can fine tune your hydraulics. So we put a lot of margin. See, I said straight length, equivalent length, then we put some 20-30%. Initial stages, we even put 30% margin. Okay. Suppose you calculate straight length 100 meter, equivalent length 200 meter, total 300 meter. We put a margin of 30% means into 1.3. So 390, almost 400. So initial estimates assume some margin like 30%. After the actual piping design is done, you can go and check your calculations and fine tune the calculations. So in any case, we don't find much of a difference. So, but anyway, before you finalize all the plant design, you do a final check and fine tune your calculations. It needs some experience to determine the fittings number. Okay.
Okay, sir. So the next question is,
somebody is waiting.
Yes, sir, I have allowed them. The next question is, sir, can you please share some typical line sizing examples for two-phase fluid flow?
Two-phase, I have to see. I may not have ready in hand. These are all done. All line sizing calculations are done using spreadsheets. So most of the companies, they have their own in-house developed Excel-based spreadsheets where the formulas are already inbuilt. Okay, and most of the line sizing spreadsheets are connected with the API 14E. I told you, no? API 14E equivalent length tables are there. They are all linked to the Excel sheet. So if you go and say enter 6-inch, 2 elbows, 1 T, 1 reducer, like that, if you put, automatically the program determines the equivalent length and the straight length we put. So equivalent length is determined by the program, by the API table linked with that. So these are all simple, straightforward calculations, and nobody does any hand calculation. Okay. So it's just entering the values and getting the results. And most companies have their own in-house line sizing.
Okay, sir. So the next question is, sir, can you please explain about SOUR service line? Hello, sir. Hello, sir. Are you there? Dear participant, let's wait for him to rejoin. There are a few more questions that you guys have asked. Dear participants, he is unable to join due to network issues. Let's keep your questions live. We will resume. We can ask in the next session. So I'm ending the meeting now. You will be receiving the email regarding the same.